these lectures aims at transmitting you with the enthusiasm that I have for data analysis. Okay? So this overview hopefully will provide you with the intuitions of how should one do data analysis. Okay? So this is the driver of my lecture. The request by the scientific organizing committee was, let's not do a very theoretical lecture in which you put theorems, demonstrations, and everything is very in the Platonic world of ideas. Let's try to apply the concept to a real problem. At the beginning, they wanted a real case. A real case meaning something from which a paper could come out with a little more effort, right? Unfortunately, we very quickly realized that would take a huge amount of time. The idea was, the proposal was, let's take a spectral energy distribution from a young stellar object, like the one I've plotted there. Let me get another image which is much more attractive. Let's use a real spectral energy distribution and try to infer the parameters of that object. So for those of you who are not familiar with these, like me, because I'm not working on these still, a young stellar object is a newly born star which still has around it a big amount of material of the cloud from which it's formed. Okay? So by conservation of angular momentum, all these dust and gas that is, Hervé, Álvaro, the guys that helped me prepare this example, if I say something which is extremely wrong, correct me please. So by conservation of the angular momentum, we expect the material, the leftover material around the newly born star to orbit the star in a disk, and this disk has some properties we are interested in. Like we would like to have to know if there is a gap between the star and the disk. We want to know that. We want, in the ideal world, we would like to know the distribution of temperatures in the disk. We know that the parts of the disk that are not exposed to the radiation from the star will be hotter, and the ones near the plane, the symmetry plane, will be cooler. We want to know the size of the particles, of the dust that makes up the disk, and how it changes in different regions of the disk, and many other things, okay? So if we look at recent, or not so recent, models of these protoplanetary disks, we would see that we have a number of parameters. We have here, I think it's like 14 parameters, like the disk flaring angle, the disk scale height factor, how the density changes with position, and an awful lot of parameters. Ideally, we would want to infer all of these, not to infer the parameters. So this is my view. I'm now showing my real face. You may want to infer the parameters of the disk. I tell you, there is no way you're going to do that. You cannot know the real parameters of the disk. Now what you want, and if you write in your paper that you found that the temperature of your disk is that or that is not exact. You're not inferring the parameters. What you should be inferring, in my opinion, in my humble opinion, is the probability distribution of the real parameters given your data. Okay, that's the way I was taught at university. A scientist should proceed. So these are my data. These are fixed. There's nothing I can do with them, except, of course, getting more data. And given this data, I should be able to give a probability distribution for the real parameters of the system. Okay, that's how I was taught at university. And that is what I will try to teach you. And side by side, I will teach you how other people proceed by providing some single point estimate of the parameters. So these are our characters in the story I will be telling you about today. And all of them, you know them already. First character are probability density functions. If your experiment deals with discrete variables, for example, if you're tossing a coin, there are only two possible outcomes, head or tails. That is a discrete variable. The variable, the outcome of your experiment, can only take two values. Okay? In that case, you don't have a probability density. You just have probabilities. The probability of the coin landing heads is 0.5 in one case, and 0.5 for tails. Okay? That's a probability, full stop. Now, if your random variable, if the random variables you're trying to infer or measure are continuous variables, then the probability is a probability density. If you think it twice, the probability that the temperature of your disk is 3000 Kelvin is 0. It is 0 because on the real line, there are an infinite number of temperatures that the disk could take. Okay? So it has to be 0. Any other value with the integral with temperature. Okay? So what really makes sense for continuous variables, imagine we only have one parameter, the disk temperature, is this. So this is a probability. Okay? Remember the dimensionality argument of James yesterday. So this has the unit of Kelvin, this has the units of Kelvin minus 1. So the product of the two is dimensionless, as a probability should be. Okay? So this is a probability that the temperature of the disk equals belongs to 3000 Kelvin minus dt over 2, plus dt over 2. Okay? So this is the reason why we need, for random variables that are continuous, we need probability densities. Okay? Now, I have here a summary of a few useful rules, the product rule and the sum rule, for dealing with probabilities. If you look at data analysis papers, you will very often encounter these rules applied in practice. And everybody assumes they are known, they're very simple, but let me go through them again. Jay explained that yesterday. So the first one is the factorization. If we have two random variables, x and y, we can factorize that joint probability for two random variables in two different ways, using conditional probabilities. So it's the probability that we find y times the probability that we actually found, given that we actually found y, we also find x. If you don't follow this in a paper, think of the probability of I being bald and having green eyes. The probability of these two events, that I am bald and have green eyes, is first the probability that I'm bald, and then the probability that, given that I am bald, I also have green eyes. Okay? Now, sometimes we all get confused with the given bar in between the probability. So, remember what Jake said yesterday, because this is very important. If we have a probability like this one, the probability of x and y given z, this is a probability for x and y, and it integrates to 1 in the two-dimensional space of x and y. Okay? I know I'm repeating myself and I'm repeating Jake's lecture, but this is very important. Only if we understand how probability densities work can we proceed and use them as just one more tool in our scientific investigation. So this is exactly what you have up there without conditioning the probability. Only we add this bar and the z behind. Okay, so if you add the bar and the z there, there's no pointer, right? And no stick. Okay, so this is absolutely exactly the same formula as above, only we are conditioning on the fact that we know the value of Z. And the other one, which is also very important, is marginalization. So if we have a joint probability for two random variables, we can always obtain the marginal probability for one of them by integrating over the other. Okay? And if we then integrate px dx, we should obtain 1, because our probability densities, by definition, have to integrate to 1. Okay. So I think I should not go into the details here. We all know what the parameters are, what the data is, our measurements as astronomers, and then the parameters may need some more explanation. We can have, so this comes about the topic of parametric inference in statistics. So imagine that you have a measurement that is supposed to come from a probability distribution. And the example I will be using throughout the day is the measurement of a flux in the Gaussian regime. Okay, I'm not talking about high energy astronomy here. I leave that to my colleagues here. I will be talking about the Gaussian regime. We measure a flux, and we have such a big amount of photons in that flux that we can assume that our uncertainties, please, not errors, are Gaussian. So, if I am in the regime of Gaussianity, I will use a Gaussian distribution to represent my uncertainty. So the probability that I will be measuring this flux or that flux will be the probability given by the normal distribution, which has two parameters, the mean and the standard deviation. Okay? Those are called summary statistics, because those two completely prescribe the probability density. With only those two real numbers, you have the probability for any possible measure. Okay? That's why we call it summary statistics. Now, we want to go from our data to our parameters. And in my perspective, we, as good scientists, have uncertainties in our data. And the way science should proceed is, again, going from data to parameters and propagating the uncertainties that is taught in the first year for a graduate student, and propagate the uncertainties correctly to the parameters you are inferring. Okay? Now, I will teach you how to do this, although Jake already showed you some examples. What I mean by model is a model of, it's a mathematical description, probabilistic description of how one parameter set produces a given data set. Okay? So this is a mapping. We have observations, we have parameters. Our model is like a map that translates parameters into observations. Okay? Our model will help us go from parameters to observations. We need to go from observations to parameters. We already know the likelihood. Please carve this in your mind, because I will be using this all the time. The likelihood is a probability density for our data given the parameters. So again, it has the dimensions of the data to the -1, inverse of the data. It integrates to 1 in the data, okay, not in the parameters. This is fundamental to see the distinction between frequentist methods and Bayesian methods. And what I, as a Bayesian, want to obtain, but this is not the revealed truth. There are thousands of scientists all over the world who do not want this, okay? So please do not feel obliged to embrace the religion of Reverend Bayes. Okay, this is not a religion. This is about how we are taught to do science and the way in which we feel comfortable doing science. I feel comfortable with this. Okay, so let's go a little bit forward. No questions so far? Okay, so this is a little explanation of the problem I will be dealing with. I've already gone through most of these. We have the star, we have the continuous disk. We may have a gap in the disk here. I will skip most of these complexities. This is an example, sorry. This is an example. This piece of Python code, the one which is above this figure, do you already have the figure in your notebooks? No? Is it not compiling? Do you have problems? It's there. Okay, so the points with the error bars are typical observations, a real observation of one of these objects. This is a spectral energy distribution. We have logarithmic scales in both axes, x and y. In the x-axis we have the wavelength. In microns, in the y-axis we have lambda times the flux. This is the way in which they usually work in this field. They multiply the flux by the lambda. Okay? And we have here, I think, could it be Alvaro a Kurup model?
Yeah.
It's a Kurup model of the star. Alvaro knows already approximately the temperature of the star, so he was not inferring, he knows it from other spectral analyses that the temperature is around that value. I think it's 3,200. So he overplots the Kurup model for that temperature. And there is an excess in the infrared, which is the emission coming from the disk. Okay? So this is the kind of things one would fit with the Rockdale models in practice. The Rockdale models are very complex. There are hydrodynamic codes that more or less simulate the distribution of the density in different parts of the disk, the temperature, etc., the emissivity of each part of the disk. Here, this is so complex that it would take ages to run the Python code. And as I said, I was aiming to have code that could be run during the lecture. So what I will be doing here, we agreed with the organizers, is that we would try to fit these with two black bodies. Okay? The reason being, we have far less parameters by fitting with black bodies, and it can make the computation of all the problems that we have much faster. So, because these are not real black bodies, we are going to do two things. The first one is we will not be actually dealing with the real measurements of Bruno and Alvaro. We will actually generate our own measurements. We will synthesize some MOX SED, okay, from our model, from our black body. Because if we try to analyze observations with a model that is too bad, we will have two problems from both. We will have the uncertainties inherent to the process of inference, the ones that I will be describing here, but we will also have problems coming from the fact that our model is not a good description of the data. Okay? And I didn't want these two effects to get mixed together. So we will, instead of using the real SED, I will generate one from these black bodies, modified black bodies, so that we can isolate the effects of the way in which we tackle inference from the problem that our model is not good enough. Now the first thing is I will not be using the real SED, I will use mock one. The second thing that I will be, the second thing I will be doing is I will be using a modified black body. So this is the formula for the black body you can find in any physics textbook. You know that not by heart. I don't think you all know that by heart, but some of you may. We will introduce a modification, that is, we will multiply the black body here, which is this formula, by a term that depends on the wavelength and is raised to an exponent beta that will allow us to have irradiance distributions which are more spread in wavelength than a black body would. If you look here at the real SED, you see that the disk can be more spread in wavelength than a real black body. So we introduced this new parameter to allow some flexibility, okay, to fit the disk. So if you look at the formulae, this is almost, and I remark here the almost, this is almost our likelihood. This is our map between the parameters and the observation, almost. It is a map because once you have the temperature of the star, the temperature of the disk, and this value of beta, you can actually obtain an SED, okay? You can go from parameters, temperature, and beta to observations. Why do I say this is almost the likelihood? I say this because there is no probability whatsoever here. With this formulae, this is a map between parameters and observations, but with these observations, we don't have a probabilistic statement of what the probability is for one data or another. With this formula, the data must exactly match the values yielded by these observations. Where does the probability come into the game? It comes when we introduce the measurement uncertainties. Okay? So if we don't introduce measurement uncertainties, if we have a spectral energy distribution that doesn't match any of these values here, of the values that you could obtain by playing with the T's, the temperatures of the star and disk and beta, then its probability would be 0. And that makes no sense, okay? Because we know we have measurement uncertainties. Okay, so as I said, this is not the actual likelihood. If we use this as a likelihood as it is, we will have a likelihood, a probability density function. Imagine you have the flux measured at this lambda, and we want to know the at 1 lambda. In this axis we have the flux at lambda equal 1 micron, for example. If I want to know the probability density for the flux at 1 micron, just by using this formula, I would actually have a delta function. It would be 0 everywhere, infinity at some value, the value given by the black bodies, and then 0 everywhere else. Okay? Now what I do is I say, okay, my physics says this, but I know from my instrument that if the real flux was this, there is a certain probability that I measure something different. If the uncertainty in my flux is given by sigma at 1 micron, I have some measurement of my uncertainty, I will say that my actual probability density will be a Gaussian. The delta function goes to infinity, but my Gaussian does not. Remember that the probability density has to integrate to 1. If the delta function is 0 everywhere, it has to go to infinity here. My Gaussian function will be something like this, with a standard deviation which is given by my analysis of the instrument, the telescope or whatever. Okay? So it is the uncertainties that make my model probabilistic. Okay, so there is yet one more free parameter, which is f here. F is measuring the relative energy emitted by the disk and the star. I think it must be related to the relative amount of mass in the disk and in the star. Is that something reasonable? Plus geometry, etc. Okay. But it's just the relative flux between the disk and the star. So that is something we also want to infer. We could have different SEDs, different spectral energy distribution, depending on the mass and the geometry in real life. Let's assume here we have a black body, there is no geometry factor. It depends only on the amount of gas relative to the star. So we want to also calibrate that. We want also to infer the relative proportion between the energy emitted by the star and the energy emitted by the disk. So this is the scenario in which I will be working during today. Most of today, not all. So we have these 4 parameters. I want to know the temperature of the star, temperature of the dust on the disk. I use this dust and disk interchangeably during the lecture. Beta, the exponent of the modified black body, and the relative energy production between the disk and the star. So I explained to you how we go from this physical model to the likelihood. Let's code it in Python. You have this block here. By the way, I think you all notice that by setting beta to 0, we actually recover the black body, the classical black body from quantum mechanics. So we have here a Python code block for the modified black body. We don't actually need to write a different function for the black body because we can reuse this block, this function, by setting beta equal to 0. And then we have the YSO model function that actually produces the SED you would obtain for a given set of lambdas. LNBS, the first argument to the function, LNBS are the wavelengths for which we want to compute the expected value of the flux, given the parameters T star, T dust, beta dust, and F. Okay? So we generate the values for the lambdas we request from the modified black body with beta equal to 0. We obtain the same for the disk emission. Then we apply the relative factor. I think here I inherited these, and this is just an approximation. We should have written here integrate. Okay, so to scale the emissivity from the disk and the star, we should integrate the energy there. Okay, but it's a sum there. I apologize for this. I should have changed. I realized this before, but I didn't find the time to change it. So it should be an integral. The total energy emitted should be the integral. So given that scaling factor between the star and the disk, we can compute the emission from the star, the disk, then we sum them together with this factor which depends on F, and then we finally multiply by the lambdas. Remember that our SED is analyzed in the space of lambdas and lambda times the flux. That's the space where you... Let me make just another disclaimer. This exercise is thought to be done from fluxes coming from magnitudes. And magnitudes are integrated fluxes, okay? We are comparing them with fluxes that come from the black body. You've asked me several times about what we as astronomers usually do wrong. In reality, so a good data analysis must be aware of all the uncertainties that come into play in the process of gathering the data, which are not only observational uncertainties, and I will come back to this at the end of the lecture. They also have to take into account, just forgot, sorry. I was talking about, the filters. They have to take into account not only the uncertainties, but also how the measurement process takes place. So if your flux comes from an integration of the flux in a certain band, you should not compare the flux that you measure in the J band with the monochromatic flux given by the black body model or the Robitaille model. You should compare them to the integrated flux coming from the Robitaille or the black body. Okay? I simplified this. I'm doing things wrong here, as I said in the disclaimer at the beginning. And this is one of the things that makes me feel very, very uncomfortable. Please, if you try to apply these techniques in your real life, in your real science. Please do match the observations with a model. If your measurement comes from an integrated flux, compare it to the integrated flux coming from the model. Don't do what I'm doing here. Okay? I did it for the sake of simplicity. If I take into account every possible detail, probably this thing would take 4 days of the school, and the code would be difficult to follow. But please don't do it. Okay? So the function that I wrote before, YSO model, is actually producing an SED for a given set of parameters. So let's try to generate an SED with this function. I will produce some random wavelengths here for the model, which are uniformly spaced more or less in the logarithmic space. Then I'm going to feed some values of the parameter, 3200 for the star, 120 for the disk. The beta exponent, I'm going to fix it to 0.8, and the scaling between the ratio between the emissivity from star and disk, I set it to 5 to 10 times 10 to the minus 3. Let's have a look at how this SED would look like. So what I do here is I run the function for these wavelengths that I randomly generated. I normalize it to have the same flux at a given wavelength. This is a normalization factor so that the SED that I will produce, synthetically produce, actually matches the flux that I see in the real SED that they provided me with at a certain wavelength. I will do this all throughout the lectures, okay? Just that, so that the units that I get are reasonable, or they look like a real SED, okay? And then I plot the SED. As you can see, these points are the real SED, and the red line is the SED that I obtain without adding any kind of errors or uncertainties from this black body model. So it's not that far, okay? We could have used the Robitaille models with 14 parameters, but I think we're not that bad with this black body, modified black body, okay? As I said, there is no probability so far. I have to introduce the Gaussian uncertainties here. And how we do it depends on your observation. In the notebook, you will have a few blocks of text where I explain to you how one writes the likelihood function in the Gaussian regime. Since we have already taken, it's only 50 minutes. I already have like 40, right? Not that bad on time. Okay, so I will not go into these details because I know you all know this by heart. This is very simple physics. Okay, you've done this as a graduate student several times. So what I do here is going from collapsed likelihood function, which is infinity adjustment value, to the Gaussian likelihood is just what I wrote here. So remember, the likelihood is the probability of your measurement given your parameters. So likelihood is the probability of a flux measurement. Imagine you have an SED composed of only one flux measurement. The probability of your measurement given a set of values, it's a normal distribution. That's what I drew here. And the normal distribution is written like here. How do we recognize this is a function of the parameters? Because this flux here, this hat flux is the measurement, the actual measurement. This F here is the flux predicted by our black body model. Okay? So this likelihood is actually telling you how far you are from the value predicted by your physical model. Okay? I will use interchangeably the word model for two things that are very different. One thing is a physical model. Robitaille has a physical model, a hydrodynamic code coupled with radiation. that is telling you the physical structure of your disk. That's a physical model. But this likelihood, I've written here, together with all other information that we may have, it's a statistical model of how your data are produced. Okay? So, unfortunately, there is this confusion of terminology. Model can be used for two things. But I think that being among scientists, we will always know what we're talking about. If anyone has a doubt, just ask. What model are you talking about? The probabilistic model or the physical model? So, we've all done this. And as I said, this is the likelihood for one measurement. If we want to find out the real, sorry, not the real. If we want to find out what would be the parameters that are most probable, that render our measurement most probable, recall this phrasing because it's very important. If you want to know what are the parameters that render your observation most probable, all you have to do is maximize this function. Okay? How would you do that? I will come back to this a little bit later, but all you have to do is explore the four-dimensional space of parameters, trying to find a maximum. Sometimes you can do it analytically. Okay? In this case, if you take your time, you can do it analytically. Why? Because this is an analytical function, and f is an analytical function, a black body, of your parameters. So all you need is time. Okay? You can do that. You can maximize and find the parameters that are up. What I have here is a proposed exercise. Let's say, I don't think it's worth. I have some proposed exercises in the notebook. Some of them are really useful. Some of them are just to keep you going. This one, I think, is not necessary because we have likelihoods coded in the notebook for many others, for a few measurements. So this is not needed. I will ask you, when we come to the exercises which I think are important for you, I will ask you if you want to stop for some minutes and do it, or if you want me to go on. Okay? So what happens if we have, instead of just one measurement, what happens if we have, as usual, an SED with many measurements? Actually, if you only have one measurement, I don't think you can call it an SED, because it's not a distribution, it's just one measurement. So here, we come back to the problem you asked yesterday about independence. So the idea here is, if we assume that all the measurements that make up our SED, our spectral energy distribution, are independent, then this probability, this F here, is written bold because it's meant to represent a vector. The vector of all the fluxes that we've measured for our young stellar object. Okay? So it's no longer a real volume, it is a vector of reals. So we would actually have a joint probability. There should be no brackets here, sorry. Well, the brackets are to represent that it's a vector. But I don't use this notation anymore in the notebook, I think. So we have the probability for a set of random variables. In general, our random variables are not independent. Okay? The case I will be dealing with here actually is a typical case where our measurements are not independent. If you have a spectral energy distribution that you gather from the virtual observatory, what you will end up with probably will be some measurements coming from the Sloan Digital Sky Survey, some measurements coming from WISE, some measurements coming from maybe ISO IRAC, some measurements coming from, I don't know, some ground-based observations in the near infrared. Okay, so the measurements, the four measurements that come from WISE, is it four? The four measurements that come from WISE will most likely be correlated, at least some of them, because the reduction procedure introduces these correlations for several reasons. But you can think, Jake mentioned one yesterday, it's the temperature of the detector. Okay, so the uncertainties in your detector, the uncertainties coming from the physics of your detector introduces correlation between the measurements. So, in the ideal world, so if we are good scientists, we should take all this into account. And if some of you belong to one of these teams actually producing catalogs, we would be extremely grateful if you could actually provide us, not with individual uncertainties of each flux measurement, but if you were able to provide the correlations amongst the variables. And this may seem like I'm too picky, and statisticians, they always like to bother us with, we've been decades working with assuming that our variables are independent, and it really makes no sense. Science progresses with these, without these correlations, but they do so, in some cases, they do make a big difference, okay? A huge difference. And let me recall something that I've been told many times, that is, if the people at the LHC had a huge bump clearly indicating that there is a Higgs boson there, they wouldn't care about the statistics at all. The statistics helps you in the grey lab, where you actually have to convince your colleagues that you detected something. Okay? If it is obvious and evident, don't bother to do MC chains and run for ages to get something. Okay? So it is in this grey lab that it makes a difference to take into account correlation in your data. So here I will actually do the wrong thing and assume that our measurements are independent. So if you recall from one of the laws that I wrote before, if I have two variables, like the flux at 1 micron and the flux at 10 micron, the probability of these, I can write it using conditional probabilities as the probability of the 1 micron measurement given the measurement at the 10 micron measurement times the probability of the 10 micron measurement. Okay? If I assume that my measurements are independent, which I know they aren't, and you should assume this measurement is independent of this. So I can write this simply as the probability of the 1 micron measurement. So it's the product of the two, right? And this is what I'm doing here. What I'm doing here is writing this joint probability of all the fluxes having the values I measure as the product of the individual likelihoods for each flux element. Okay? This, since it's the product of many normals, I can write it as just one normal, but a multivariate normal distribution. Okay? We have univariate, unidimensional normal distributions. Those are the distributions you are used to see. The one I wrote a few lines above, but we can write a multivariate normal distribution just in the same way, except that whenever we had a mean value, which was a real, now it's a vector, the mean is now a vector, and the standard deviation becomes now a matrix. It is called, well, the standard deviation, not exactly, it's the covariance matrix, the square of the standard deviation. It becomes a matrix, which in this case, where we have the assumption of independence, this matrix is diagonal. And we have in the diagonal, one by one, the values, the uncertainties in the individual fluxes. Okay? There should be a backslash here. Now, this is very important, and Jake already explained some of this yesterday. Now, the likelihood, I wrote above, is a multivariate normal distribution, which is written like this. For the case of a diagonal matrix, it looks like this. Now, if you look at the exponent, what you would have is the square of the difference between the measured flux and the flux predicted by the model. Here, it's the flux measured minus the flux predicted by the model, divided by the uncertainty. It's all squared and sum. And this
is your product in the right place, in the likelihood?
Here, this product
should apply to the whole thing, not it's below the line. It should be.
What do you mean?
It should be the whole thing. Each term
You multiply each term, keeping the normalization as well as the exponent for each of the terms. The product should be up.
No, it's if you actually have the product for each individual likelihood, you can, because you have many exponentials multiplied, you actually have these where there's a sum, okay? And the constant terms, you have one of these for each individual likelihood. So you actually have a product of n uncertainties, and here you have, because you have many products of the square root of 2 pi, you have to raise it to the power of n. I think it's, I may be wrong with it. I think it's right. So this is an old friend of yours, of us. We all use it, and we use it all the time, okay? We do chi-square minimization. And I'm pretty sure you all know why you do it. But I will go through the assumptions that underline the usage of chi-square minimization so that you realize what you're doing, what we are doing, because I do it myself as well, okay? And most of the time, we are right. Some of you actually asked me to, there should be a lecture of the kind of things we do wrong as scientists. We don't have a background in statistics. Please tell us what we're doing wrong. Most of the time, you're not doing things wrong. Most of the time, it's just that you're not aware of very powerful tools to solve problems. And sometimes, what we do wrong is we are not aware of the assumptions of the methods we use. And sometimes they don't apply. So that's all. All we have to do to be good scientists is be aware of the assumptions under which we can use certain methods and test them, check that we are in the good way. But if you are looking at STDs, you're very well by doing chi-square minimization. What are the assumptions that underlie the usage of these? Assumptions is that we are dealing with Gaussian errors, which for a spectral energy distribution of a young-stellar object, it is correct. And here I've written it like this, assuming that we have independent measurements. Our measurements are not correlated. But if you have measurements that are correlated, there is a chi-square as well. Okay? It's only that the chi-square will now be not the sum of these individual measurements. You will have a matrix product. Okay? Your fluxes will be a vector. Your covariance matrix will be a matrix with values outside the diagonal. It's a symmetric, positive, definite matrix. So it will change a little bit. But again, finding the maximum likelihood, and I will say again this sentence that I should carve in my grave, finding the parameters that make your observed dataset most probable, it's just a problem of minimizing the chi-square. It's as simple as this. It's the function, the likelihood function. You want to maximize this probability, and in order to maximize this probability, you have to minimize this guy here, which is a chi-square. That's all fine. It's no problem. The problem is, A, if you're trying to feed high energy measurements where you have only a handful of photons hitting your detector, you cannot assume Gaussian errors. And if you do chi-square minimization, you're doing wrong. Okay? And you're using the wrong model for your data. And it will come as no surprise that you do wrong inferences, as simple as that. Another example where we cannot use chi-square in general, is trying to feed histograms with the Gaussian uncertainties. A histogram is a counting experiment. An accounting experiment does not yield real values, and the probability density for the counts in a bin is not a Gaussian. Again, you should probably be better off using a Poissonian distribution. Okay? But that's all. It's not a lot more about chi-square. I see many people excruciated because they think they are very poor scientists. They only use chi-square. Sometimes it is the right tool for the right data. Okay? So this is how, one variable this one, chi-square. I'm now looking at the random variable that you construct by summing many Gaussian variables. This thing within the parentheses is a Gaussian variable. Fi is not a Gaussian variable. It's the flux predicted by the black body, full stop. But this, the measurement, is a variable that is distributed according to a Gaussian. So this thing in parentheses, if we actually computed this for many SEDs, we would see it's distributed like a Gaussian. If you sum the squares of many Gaussian distributed variables, you get a value of this chi-square which is distributed like this. We will do this experiment at the end of today. We will generate many SEDs, many SEDs. For each one of them, many SEDs including the Gaussian noise, okay? We will compute for each one of them the value of chi-square, and we will do a histogram, a very simple histogram, trying to see how is this chi-square distributed. If we did, we would see something, and we will see something like one of these curves. It will be more like the yellow one, okay? This depends on the number of measurements, on the number of degrees of freedom. Excuse me if I skip this number of degrees of freedom, because I will deal with this in more detail in the model selection block. Okay? So for the time being, let me just say that it sort of tells you the complexity of your model. And in this case, it is almost, approximately the number of measurements. Okay? Number of measurements minus something. So what we are doing here is compute some chi-square and choose the value that minimizes our chi-square. Now, let's do it for our young stellar object. As I said, what I will be doing in the following is generate one synthetic SED. It's a code that is just above this figure here. I've set the seed of the simulation so that all of you get exactly the same plot. It should be the same plot. So I actually fixed the values of the parameters to generate. I'm here like God, sitting on a cloud. Right? So I'm going to generate one observation, one log observation, for a system with a star of 3,200 Kelvin temperature. My disk will be 120 Kelvin, just on temperature. This is a simplified model. My beta, the exponent of the modified black body, will be 0.8. And this F value that gauges the difference in emissivity between the star and the disk is fixed to 0.005. I just neglected the values. Okay? And then I add Gaussian noise with a given prescribed values. I could have chosen a random standard deviation for each flux measurement. I took the proposal by Alvaro to just fix it to a 5% of our measurement in lambda f lambda. Okay, so the y-axis, my SED is defined in terms of lambda times the flux, and I'm assuming that my uncertainty in this y value, in the measurement that I make, is a 5%. If you think it twice, and this is something we should always do, the uncertainty in lambda times flux, if we assume that our wavelengths are measured with infinite precision, which is what I'm doing here, this means that this 5% is lambda times the uncertainty in the flux. Okay? And all of this has many implications. I just inherited this definition, and it's fine as long as you believe this is a good case. If you apply this methodology to your own problem, never do it. I think this is unrealistic. Okay? This is just a prescription like any other could be. It's just simple. It can be written in just one Python code, a line of code. So it's simple. But never do that because I think it's unrealistic. Right? And you all know that. So here, oops. I generate these mock SED. I define the log likelihood. This is just the chi-square that I was defining above. Okay? It's the observed flux minus the flux predicted by the model divided by the error in that observation. I square that, so that would be the chi-square. I'm neglecting here the constant terms. Okay? There is this normalizing constant in front of the exponential. It depends on the uncertainty, but that term will be the same for all the possible SEDs that I can consider. So, so this is a function that is actually giving me the value of the chi-square. Okay? So if I define the parameters of my model for one value which I just made up, 4,200, blah, 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 I can print the log likelihood. The logarithm, the chi-square value. Okay? So if what you want to do is to, this is my mantra, obtain the parameters that make the data most probable, all you have to do is minimize the chi-square. You've done this so many times. I shouldn't be doing this here. It's really stupid that I waste my time going over something you can do with your eyes closed. So this is what you're all used to obtain, except for one extremely important thing. So you all do this, right? You compute the likelihood for a grid of values. What I did in the Python code above is to compute the likelihood for, I don't remember if it's 10 values or how many. Check. No, the grid size, it's 100. So I divide, I decide that the temperature of my object will be in a certain range, which I define to be between, okay, 80 and 150 for the disk and beta, between 0.2 and 1.2. If I recall correctly, what I do, and this is my point, this is very important. In order to produce this plot, this would be the distribution of likelihood in a two-dimensional space. I have the temperature of the disk in the x-axis between 80 and 150, and the beta exponent between 0.2 and 1.2. Okay? This is a very convenient plot because it shows you in a very intuitive way how does the likelihood vary with your choice of parameter. And you see this is what many people call a convex function, meaning it only has a minimum. Chi-square only has one minimum, and it behaves reasonably well. It looks like a Gaussian. It's a little bit curved. It's not very well appreciated here, but a little bit of a banana-like shape. But it is a convex problem. What's the problem here? The problem is our likelihood is 4-dimensional. How did I get from a 4-dimensional function to this 2-dimensional plot? I did it by fixing the values of the other two parameters. So this is how the likelihood looks like for t equal 3,200 and f5 10 to the minus 3. The right values, okay? This is something that every frequentist has to do. If you go frequentist, if you only want to hear about likelihoods, which is a very respectable approach, right? I'm not criticizing here. I will talk about the caveats of going Bayesian in the next section. But now I'm explaining to you how does it work the maximum likelihood. When you do minimum chi-square, you're doing maximum likelihood. That's what we all call frequentism. Okay? So when you go frequentist and actually stay with just one value of the parameters, which maximizes the likelihood, if you want to look at a 2D plot at the distribution, you have to fix the parameters to fix the value of the remaining parameters. Okay? And you fix them to the maximum likelihood. I have a little piece of code below that show you how to compute the maximum likelihood. Yeah, it's here. So I'm going a little bit too fast. So let me stay here. So, but keep in mind that this 2D plot is obtained by fixing the other two parameters, the stellar temperature and the F value. Okay, so this is what we have. I have a small section here. I have a small section here on what would happen if your uncertainties were correlated. Your covariance matrix then becomes non-diagonal here. This is what you would get here. The problem is what is often called chi-square. If you call this chi-square, you're doing wrong. You can minimize these. That's no problem. That's what I said before. You can, to maximize your likelihood, you can minimize this exponent here. That's pretty much a good thing to do. But then, this thing here is no longer distributed as a chi-square. So don't call it chi-square, call it something else. A chi-square, it's the sum of many random variables, of the squares of random variables that are Gaussian distributed. Okay? In this case, we have something which are not squares, because we're multiplying, the cross terms in these covariance are multiplying the observations in one and the other. So you can minimize the chi-square, you can minimize the exponent, you can minimize the exponent to maximize the likelihood, but don't expect this value here to be distributed with a chi-square distribution. And this is important for model selection. I will come back to this when we try to decide which model is better justified by our data. Okay? This is another thing that is often a misconception.